So now that the training is complete, the results can be applied to the entire sequence. And to do this, we're going to use an inference node. This node reads the .cap file and applies the effect that was learned from the dataset to the entire sequence. Add an inference node to your node graph. You can use the button in the CopyCat properties, or just create the node in the usual way. Browse to the .cap file in the model file field. If you've used the inference node button, then this will be auto-filled with the latest cat file from your specified data directory. You may not want to use the latest one, so you can change it manually if needed. View the inference node to see the effect applied to the current frame, and you can skip through the sequence to examine the results on different frames. Inference applies the model on each frame, so you may not be able to play back the sequence in real time, depending on your machine's GPU and RAM specifications. You can use the Optimize for Speed and Memory button in the inference properties, but this may cause artifacts in the viewer, so just bear that in mind. It's unlikely that the result is a perfect garbage mat at this point, and we will need to do some tweaking, but we've managed to produce a really good starting point. And as I mentioned before, you can play around with the settings and retrain the network if you want, to find out what works best for your machine. So I've run another training session where I increased the number of epochs to 40,000, just to show you a comparison of how the training can be improved just by leaving it running for longer. So here you can see the difference between the 10,000, 20,000, 30,000 and 40,000 epochs. You can see there's some artifacts in the background and around the edges that improve the longer the training ran for. However, there's not much change between the 30,000 and 40,000. Remember that training for longer will not always continuously improve your results. I could have also used a larger model size or crop sizes to possibly get a better result, but I used the default values to produce a starting point, and this way I can make changes and know how each option affects my outcome. To apply the map to the sequence, I'm going to use a copy node to grab the red channel from the inference node and copy it to the alpha channel of my source sequence. I could also use a shuffle node to do this. You can then add a premult to see the map affecting the sequence. To speed this up, you can write out straight after the inference node or at any point, and then the result can be played back closer to real time. As mentioned before, if your result doesn't look as expected, the first thing you can do, if you're using two append clip nodes, is check the order of your input and ground truth images is correct. This is a common mistake, but it is a really easy one to fix. You can also try adding new image pairs to the dataset to contain more diverse examples. And this is the first thing that I'm going to do before retraining, because from looking at my result, I can see that there are some issues where the network hasn't learned what to do in certain places. For example, when more of the woman's trousers are showing, as I haven't trained the network to know what to do when so much black is showing. So I could rotate this frame and add it to the dataset and then try the training again. It's also not looking quite right when her headphones overlap with the sky, possibly because they're both white and they're hard to distinguish between, and the network hasn't been taught how to react in this situation. To avoid rotating more frames, you can make fake data to add to your dataset to represent instances that you want to include when training the network, but that may not necessarily exist in your original sequence. For example, instead of rotoing a frame where the woman's headphones are overlapping with the sky, I could duplicate an existing roto and place the woman in the right position so that there is some overlap. This immediately provides the network with so much more information, and I didn't have to spend any time rotoring more frames. As long as the fake frames contain a combination of the elements from the original sequence, then they'll be helpful when training the network. You can't use images in your dataset that contain completely different elements. You can also try cropping, rotating, flipping, grading, and repositioning the image to improve your dataset. You can have a play around and create a really diverse dataset, then train your network again, and you should see improvements in your result. If you have had to make adjustments to your input or ground truth images, you will need to restart the training. In the advanced properties, CopyCat lets you use a checkpoint or a weighted model pre-trained to perform a task that you can use when training. This means if you choose checkpoint, you can enter the cat path from a previous training session to weight to the training from that existing cat file. This way, the second training will be weighted to perform the same task as before, which can speed it up. There are also pre-trained model options that weight the training towards deblurring or upscaling, but I'm not going to go into these options in this video. So now I'm going to train the network again, now that I have added new images to my dataset. At this stage, I'm not going to change any of the other settings, as I only want to change what's necessary. So I'm going to let the training run a little first. You can always stop your training to see how it's progressing and then start it again to pick up from where it left off. While the training is stopped, you can increase the number of epochs before starting it again to let the training run for longer to try and achieve a better result. You don't have to stop the training manually. If the training runs to the end of the total steps, you can still increase the epochs and resume to continue the training. Alternatively, you can stop the training if, for example, you're using the preview to monitor the progress and you're happy with the result that you can see. The training doesn't need to complete the total steps to produce a good result. So I'm going to leave this to run and see what result we get. Training's finished and the result is better than before, but still not perfect. But we can use some other techniques to improve the mat even further. You can use the thresholding and filling techniques to further refine your mat. Thresholding involves adjusting the black and white points with a grade node to remove any artifacts in the background of your mask. And filling involves using a roto or rotopaint node to remove artifacts or fill holes in your mat. Here's some examples of various training tests that I ran to experiment with what settings might produce the best results. I found that adding more images to my dataset using fake data helped to improve my results the most. Adjusting the model and crop sizes didn't make a huge improvement, and they didn't help enough to account for the extra time taken for training. An epochs value of about 30,000 was sufficient for training the network to achieve good results. I did test up to 50,000 epochs, but this didn't make any noticeable improvements. I did use thresholding and filling techniques to improve my garbage mat as well. As I said before, improving your results will depend highly on your machine specification and the task that you're attempting to carry out. Something that works for my machine may not be effective for yours, and something that improves a garbage mat result may not improve the result of beauty work or deblurring, so it will take some trial and error. And you can continue to refine your result until you're happy. Although there is some tweaking to be done, you can see how much quicker it's been to create a mat using CopyCat than it would have been to manually roto this whole shot. Thank you for watching. I hope you've enjoyed this series, and to learn more, head to learn.foundry.com/Nuke for the user guide and many more courses and videos.